Good day, guys. So, by today we'll be discussing about another interesting protocol, BBM92, and again it comes under the QKD roof, quantum key distribution. So, initially we have started looking from BB84. Hope you remember, right? So, it's a first protocol that has been exclusively quite invented or designed to make the quantum channel to have a secured quantum key distribution. So then we have seen about E91. It's another protocol that is also used for this QKD process. So in continuation, we'll be seeing another BBM92, and this actually the protocol keyword itself states that it's an extension of BB84, as because it also have the same BB. Of course, as you guessed right, it's a Bennett and Brassett, the two inventor, but along with another inventor called Mermin, right? It was invented, or it can say enhanced version of BB84, and given in the year 1992. So as we already aware that this BBM92 and E91 both use an entangled photon. So which means a pair of photon will be created either from source, that is a photon source, right? We can say it's a photon source, right? A pair of photon will be created, and that will be shared to Alice and Bob. Or we can also say this photon source could be Alice himself itself. So he'll be having one photon, and the other he'll be sharing to a Bob, right? Other photon. So this is how the pair of photon, entangled photon, is used. Just a recap, right? We do know what is entangled photon, right? We always know what is entangled photon. So if we measure one photon, then that will help us to determine what is the other one. So that we just keep on speaking about a pair of red and blue balls in a box, right? If you open a one box and the other box is kept very far away, so this one box measurement will say what will be in the other box, right? We always know. And glove, a pair of glove, if we come to know that this particular glove is a right hand glove, then the other glove should be a left hand glove. So this is what the entanglement meaning, right? So just a boring recap on it. So now we straight away pitch into this BBM92. So along with the Merman, all the three inventors have introduced this entangled photon to be used in order to make the QKD to be very successful. But they use the strategy or technique called QBER, is the quantum bit error rate. So they try to compute the quantum bit error rate. So based on that, they will find out that whether the key has been eavesdropped by the stranger, and obviously we know it's an Eve, that culprit girl will be always doing eavesdropping of the personal message between the Allies and Bob, right? So they used to have a common threshold also, right? Threshold value, right? Usually they say 11 percentage. So if it is the QBR, if it is calculated and it is less than 11 percentage, then it's secure, right? Then it's secure, right? If it is greater than 11 percentage, then it's not secure, and it will be discarded. The entire protocol will be discarded, and they'll be just doing it once again. Right. So now we are trying to calculate the QBR. So before that, we understand, right? It's a entangled photon, so the representation will be always 0, 0 and 1, 1, right? We know that, right? So because an entangled photon, so one qubit will be having 0, 1. So if it is 2 qubit, we'll be having a 1, 1, right? 0, 0 and 1, 1. So coming to what are the bases, we already know it's an inspiration idea from the BB84, and BB84 is an inspiration idea from that Stephen Weisner. Hope you remember, it's a quantum money, right? The same way around. So here they'll be using a two-axis Z axis and X axis. So we do know Z axis is rectilinear, right? It will be used usually by the plus, that is, right, a vertical line and horizontal line. And similarly, X axis is a diagonal, right? We do have two diagonals in order to represent. And again, this we can say, right, vertical line to represent 0, horizontal line to represent 1, the same way around, one diagonal to represent 0 and another diagonal to represent 1, right? And this is called Z axis, and it is usually represented in KET 0 and KET 1, and this is called X axis, and usually represented by KET plus and KET minus. So just remember a formal, right, a formal notation we used to say. And technically we can say it's in psi, KET psi, and it is represented by KET 0 plus KET 1, 1, and it is represented by root 2, right? Guys, hope you know this root 2, right? Just have a quick look on this root 2. What is this root 2? It does a normalization, the process of normalization, because we always need it to be, right, the final, right, the final state to be equal to, right, 1 bit. So we need a normalization. For that only we are using a root 2. Just remember this and don't want to confuse. It's like a formula, right, in order to do a normalization. Now we straight away pitch on to an example, right? Like we have this guy, right, Alice and Bob. Now this guy is using an Z axis. If this guy is also using an Z axis, now he is accepted. If this guy is using an X axis, this guy is also using an X axis, then the key is accepted. If this guy is using an Z, this guy is using an X, then the key is discarded. Again, this guy is using an X, this guy using an Z, right? Again, the key is discarded. So, to be more precise, right, we can say Alice, right, Bob, right, and key. If Alice is using an Z axis, right, and is having a 0, and Bob is also using an Z axis, then he'll be measuring 0. Then of course he is correct. If Alice is using an Z axis and he is saying is transferring a bit 1, and Bob is also using an Z axis and he'll be measuring the 1, the key is accepted. If Alice is using the X axis and if he is saying plus, and if Bob is also using an X axis and if he is saying, and he will also see its plus, then key is accepted. If again Alice is using an x-axis and he is having a minus, this Bob, if he is also having an x-axis, then he will find a minus. He is accepted. Now all the other way around, right? If Alice is using an z and he is measuring as a 0, right? If this guy is using an x-axis, then what happened? Then he will be having a random. Why? Because this is x, this is z, this is x, and other way around. If he is using an x, it may be a 0 or 1, just for consideration 0, and this guy is using an z axis. Using an z axis, then again this also became a random. In this both case, we are discarding the keys. So this is how the entangle photon will be measured. Now we just straight away pitching into the QBER, quantum bit error rate. So the computation will be, right, QBER is equal to total mismatch by total comparison. It's simple, very simple, right? So QBER is equal to total mismatch is equal to total comparison. Just look at the previous example. How many comparison we have did? So 1, 2, 3, 4, 5, 6, right? We have done a 6 comparison. So how many mismatch we do have? We said that it's a 2 mismatch, right? We said that it's a 2 mismatch. Now 2 divided by 6, right? What happened? That it's 2 divided by 6, 200. So it became a 33%. So QBER, quantum bit error rate, is 33%, which actually illustrate it's an eavesdrop message, because the threshold is always expected less than 11%. So right, so hope you understand, right? This is how the QBER is used in the BBM92, right? In order to obtain, right, whether the Eve, the culprit girl, right, have eavesdropped the personal message between the Alice and Bob. So we'll be always noting down how many mismatch, right, by the total number of comparison that has been made. So if it is less than 11%, then the entire protocol will be retained. If it is greater than, then it will be decided that it has the eavesdropping, so it will be discarded. So it's easy to understand this BBM92.